Okay, hello everybody. Good to see you. So, as already discussed on the chat, it's a busy morning here in Amsterdam. I think you're calling in from lots of different places. I see people, at least I think from the Netherlands, from China, from India. So, good morning, good afternoon, good evening, wherever you are, and very happy to see you. We have roughly 1,000 participants, right? So it will get a bit busy. So I hope if you have questions that I can answer them. Not 100% sure because there may be too many, but I'll try to do my best. So with that, let's dive in. We have a new topic. In the past, we had blockchain, AI, metaverse, and this time it's Industry 4.0, right? So it's a different topic. Very interesting, I think. So super intriguing topic to think about, but also a bit hidden for a lot of us, I think, how we manufacture stuff and how we actually build the stuff that we consume. Is not so obvious, right? So this will be something I think different than what you're used to normally. Okay, let's go in. So Industry 4.0, or you can call it smart manufacturing. It's about how we produce stuff as a species, right? So how do you make all the stuff, whether that's bottles or iPhones or televisions or cars, right? So how does that process work? And before we go in, I would like to know from your side, how familiar are you with this topic? And just be honest and put it in the chat. How much do you know about this? 1 means I know very little, and 10 means I actually know quite a lot. So put your number in the chat. And by the way, of course, you will get the slides, you will get the recording. And if you would like a certificate, then please go to the link I shared in the beginning of the chat. Don't email me because we tried it in the beginning, but we get hundreds of emails. So just go to that link and you can get a certificate there. But slides and recording will be provided. Okay, I see a lot of numbers, quite some people saying 1 or 2 or 3, but also some 5s and some 6s and some 7s. So quite a big range of numbers here. So, okay, interesting crowd. Let's go in. So maybe to start with the basics, right? If you say Industry 4.0, you say manufacturing. So I think the first question is, what do we mean with manufacturing? What does that really entail? And manufacturing is a process of production, right? It's a flow of goods where you add value in the factory. That could be anything, right? It could be bottles that you make from plastic. It could be bricks that you make from stone. It could be iPhones that you make from multiple suppliers. But production creates wealth, right? So production is an extremely important thing for countries. And this is about mass production. This is about repeatable mass production of goods and services. So I've been a consultant in the past, and consultants work with KPIs, right? Key performance indicators. And in manufacturing, typically you have 4 main KPIs, right? 4 things that you try to optimize your factory for. And one is, of course, quality. So let's say you make these bottles. Every defect bottle that you make, you can throw away, and someone will need to filter that defect bottle. So the percentage of high quality products, very important. The speed, the throughput, how many can you make per hour? Also very important. The cost price, of course, right? What's your cost price per bottle? But also the flexibility. So what if we, for example, this bottle has a Kimo logo. What if we want a different logo or a different top? How long will it take to rebuild that entire value chain before we can do that? So it's a combination of those things. You optimize for those measures. That is the logic, the essence of manufacturing. And of course, they are not completely compatible, right? So maybe the highest quality you will not get at the highest speed, right? So you have to make choices where you do something and where you don't. But this is how that game functions. And in practice, you could say, hey, it's an optimization game for something called OEE, which is the overall equipment efficiency that you have. So you build an entire factory. Some factories can be extremely expensive, like a steel factory can be 1 or 2 billion euros to build. And of course, you want that factory to run day and night, right? So here are your 3 main things that we typically look for in a formula. Availability, it should run 24/7, right? All the downtime you have is time wasted. Performance rate, if your machine runs at so many cycles per minute and it goes slower than that, you lose, right? Quality, same thing. So availability times performance rate times quality is called OEE, which is the main metric that is typically used. This is an example of a steel factory, so very old school. We actually have one of these factories here around the corner. What typically happens is they run 24/7 and they have to be active 80% of the time or more, which is day and night, including the weekends, right? And if that is not happening, then the factory is losing money. And if something breaks in the chain and things go down, so you call it uptime and downtime, that is extremely costly, right? Because the whole chain can be impacted by one error somewhere in the chain. Okay, then with that basis, so you know a bit about manufacturing, you know about the optimization for specific elements. What is Industry 4.0? So that's the way we produce stuff right now and in the next decade. But what are we talking about? Well, it's the infusion of digital technologies such as AI, 3D printing, Internet of Things, right? Which are sensors that can provide data, and AR, VR, augmented reality, virtual reality. So it's those technologies coming to manufacturing. Why? Well, obviously to produce goods with higher quality and at a lower cost price, which is always the goal in manufacturing. In an ideal world, right, the entire value chain where you put stuff in and in the end where you derive the higher quality product is completely filled with sensors. Therefore, it allows continuous analysis of the data. Of course, that should be low latency, right? 5G or 6G kind of connections, which means that you have instant insights, not a month later. And that means you can act right away if something doesn't go the way you planned. But there's a bit more to this, right? It's next to this sort of factory of the future. It's also about new business models that you can make with this kind of factory and new ways to make products like mass customization, right? Everybody has their own set of Nikes. Everybody has their own specialized toys, right? Because now with the flexibility we're now building in, you can actually have both mass production and mass customization, but we'll get to that later. Industry 4.0, by the way, is German. It's a German word for this trend, but this trend is, of course, also happening in the US, in India, in Japan, in France, and in China. And everybody has a different word for it. In China, it's Made in China 2025, right? In Japan, it's called Society 5.0. Whatever, it's the same thing, right? It's a digital technology infused factory of the future. Before we go at all the technologies and all the new service models, etc., that are attached to this, I would like to take a step back and look at manufacturing the way it came up in the last 200 years. And I think that story, at least for me, is fascinating, right? So how did we actually start to make stuff in mass production the way we do now? And this is the typical chart you will find if you open a book about Industry 4.0. It's always something like this. So you have Industry 1.0, 2.0, 3.0, and 4.0, which is where we are now in. And 1.0 is the first mechanical production, where we first started to make sort of large level machinery in a factory. And of course, then you're talking steam engines, right? You're talking 1800, the first steam engine that was usable was created by Richard Trevithick, which I think is an Irish guy, if I'm correct. And the first steam locomotive, like the sort of mini train I'll show you in a bit, is 1802, right? So we're talking 200 years ago. It's not that long ago. But at this point in time, these machines were very inefficient, right? And technically they would work, but they are not optimized. You would still have wooden logs inside that you need to light with fire, with water that you need to boil. So the whole thing is pretty mechanical. And people did not work the way they work now in factories. Now you have this chain where everybody is specialized in one function. But at that point in time, you had a couple of people building the entire machine, right? So there were multi-skilled, quite complex things. And that meant that in the end, you could make something, but only very few people knew how to repair it. So you could not send it back to the factory, of course. And the efficiency of those systems were very low. So let me show you an exact replica of the world's first steam locomotive and look for a couple of things. Compare it to your current bicycle, scooter, car, whatever you drive, and look at the amount of power it can produce for the weight of the machine, right? Here you go. So this is a guy in the UK who made the exact replica of the first steam locomotive. And this is the speed it can travel at. I think he can probably walk next to it. It's very heavy. It's all made of steel. I'm not sure how far it can go, but my guess is We're talking 10 kilometers or maybe a bit more, but not too far. But this is 1802. This is the first sort of engine, the way we think about engines. I think if you're not careful here, then you might also lose your hands in the process. But this is 200 years ago, first engine with that kind of efficiency. Then, of course, we went on, right? So especially as of 1908, and this is a classic thing, Ford made the Model T. Model T is the first mass-produced car. They started in 1908. They ended in, I think, 1927. They made 50 million of those cars. And this is the first car that is really produced in a factory with a assembly line where everybody would do their own little thing, right? And then lots of people would be in that assembly line. And there's a famous quote that links to this time. You can have it in any color as long as it's black, which means that we do mass production, but you cannot change anything in the product, right? Your car is your car. And of course, you can change the paint yourself, but the factory just spits out the same things every time. And this is also the first moment where people started to realize, hey, it might be smart if we specialize in different tasks. So maybe Rens is a really good painter, but Krishna is a really good guy with the engine to do a specific thing. So Krishna will only do that, Rens will only do that, and Deepak will only do that, right? So you get this first optimization layer where you see people specialize. We call that tailorization. It's based on the Taylor model. And that makes things more efficient and makes people a bit more narrow in their skills. Another thing nice to notice for everybody that loves engineering or is in engineering school, right? This is the first time when engineers became really valuable, because the way Ford went out is, you can see this here on the right, they went out with a $5 a day package, which was a lot of money, right? So we technically said everybody that works in our factory is going to be paid really well because we really value engineers. And that actually meant some of them could buy a Ford Model T themselves. So this is the car, the first mass-produced car. In my view, it looks pretty uncomfortable, right? Because the tires are very, very thin, but it has a lot of the same things that we have today. In the beginning, if you wanted to start your car, you would use this hand crank, right, to get it going. Later, of course, it became a battery. It went like 65 kilometers per hour. So it was not too bad. It used 18, maybe a bit less liters of fuel per 100 kilometers. Currently, the best practice is 3.6, right? So we got like 5x more efficient over time, but it's not such a bad product, I think. The only issue really was if you went up a hill, then because of gravity and there was no fuel injection, your engine would stop. So the only way to go up the hill is to go backwards. So the gravity would still push the fuel into your engine. So it had a couple of design flaws, but a lot of those things were actually quite solid. And this then sold 15 million cars and it was the first mass production. And let me show you, I was able to find a video where you can actually see this. And I think what's interesting to see here, because I'll show you the Tesla factory and that is happening now, 2 minutes from now. But look at the amount of people actually involved, right? Every item that is there is made by people, right? So there's no robotics, there's no IT, there's none of that. And look at this chain is moving at maybe 0.5 kilometer per hour. But if something doesn't work, if someone screws up their job, that whole chain would stop, right? Which means that everybody would have to wait. So this is the beginning of this process. It worked relatively well, but it had a lot of issues with it's very labor intensive. If the chain would stop somewhere, then maybe 500 people would be doing nothing until it was resolved. But this is the factory that we built in 1908, right? This is the beginning of this process. Question for you, and please put it in the chat. How long do you think it would take to build a car in the beginning of this situation? And I'm not talking how long does the chain work, but how many man hours would you need to build the first Model T in 1908? And the same question is, how long do you think it took them in 1927, which is when the last car was produced? So give me a couple of estimates. I see 3 months, so 6 months. So how many man hours would you need to build this car in the beginning of the process, and how many at the end? also 6 months. So 6 months of man hours. You guys are pretty pessimistic about this process. I was more optimistic when it was 48 hours, 100 days. Okay, so the estimates are, I think, all over the place. 2 months, 1 car per 1 day, 72 hours. Okay. Okay, thanks, guys. I think the numbers are anywhere between 100 hours and 6 months. So the answer is in man hours. In 1908, it took them 12.5 hours to build a car, right? So that's 12.5 hours people hours. And in 1927, it took them 93 minutes, right? So you can see also this optimization of how much time should we spend in, how much can we automate, how can we speed up this process. So it really improved quite significantly over time. Today, and that's a bit of a funny note, Tesla, for example, needs roughly 10 hours to build a car, one of their electric cars. And Volkswagen is still at like 30 hours. So there seems to be a big gap still between them and how fast they can move. Of course, electric vehicles are still quite new. So Ford had 19 years to practice this car, and these cars are still only a few years old. But you can see this type of metric is how you measure your manufacturing efficiency. Okay, let's continue. So then Industry 3.0, and this is where I think this is more normal for us. This is where you have IT. So you have programmable logic. You have factories that you can see around you. I'm pretty sure all of us have seen a couple in the neighborhood. And this is also where we have more new principles of how things should be done. And quite some of that is Japanese. So Toyota Production Service or Systems, the TPS, right? That is where most of the companies learn from, because the Japanese at this point in time with Toyota were extremely efficient and were just better at the job than a lot of EU and US companies. And they had new principles like just in time. So a specific item would arrive just in time to be fed into the product. So you would not have a big stash of screws, for example. Kaizen, which meant that we make it 1% better every day, right? And everybody's responsible for that. So it's an iterative process where the whole chain is optimized every time. Waste elimination, which means everything that's not valuable in that chain needs to go, and everybody can identify waste. So this is a more team-heavy, process-optimized flow with IT, with the first robots, and with visual management. And what I think you will know is Toyota, but lots of other cars also came up with something called a platform, right? So many products are actually platform products. And that means that there is a common base. In this case, this is a Toyota platform for a car, right? But actually that platform is the same for lots of Toyota cars. And Nissan has the same, Volkswagen has the same, right? Why would you do that? Well, engineers get trained in that one platform. They understand that platform. And the platform is mass produced, of course, right? So it's easier to buy in bulk. So therefore, it's actually easier to make new products once that platform is really solid. If you need to have a new product, you can be faster because your platform is the same, but you build a new car on top. It's easier training for the staff, right? And lots of products now actually work like this. For example, a Black & Decker drill, right? These are these drills you use in your household if you want to build something. They have 120 drills, but it's the same engine, right? So it's exactly the same stuff on the inside. Volkswagen, Audi A3, Volkswagen Golf, all these cars, same platform, different car. So this kind of optimization kicked in, and that became quite famous, right? That is how a lot of companies still think. Then let's move to what you're here for. So 4.0, what is the essence there? Well, it's the digitalization of this production of these factories, right? Where machines can function autonomously. They can see the world through sensors, maybe temperature, maybe vibrations. There's lots of different sensors you can put in. And they can connect either with human dashboards or with other machines. And therefore, of course, they can sync, right? So that means that a lot of work can be automated. And most of these things will have a digital twin, which means you have let's say a car in the real world and you have a car in the virtual world, which is a twin of the actual copy. And you can optimize virtual products before you optimize the real thing. So that logic that you have a virtual copy and you can test new software updates, etc., on your virtual copy before you roll it out, that is quite common in this space. It's also the moment where, because it's so automated, you have more room to change things quickly. So it allows for mass personalization. And that will also change the business model. But this is the essence, right? It's the infusion of sensors, technology into this mass production cycle. How does it look like? So you just saw Ford, but now let me show you a recent Tesla factory. Oh, sorry, that is my Evernote update. Okay, I think you get the gist, right? It continues for a bit. You can find more of this online, but I think the contrast between what you saw with Ford 100 years ago and what you see now with Tesla, I think is quite stark. So I think you get the message. So a couple of questions I see that popped up. Is the recording shared? Yes, I'll share it somewhere later today and send it to your email. Flexibility, can you please elaborate? That's a smart question, because what happened in the past, once you have that whole chain set up, right, and think back of this Ford Model T chain, you don't have a lot of flexibility, right? Because everything is optimized for that particular car you're going to make. And the car is always black, has the same wheels, has the same steering wheel, and everything is the same. Now what you can see, like once, for example, you have a platform strategy. So the underlying engine, the underlying sort of skateboard that the car sits on, the underlying tire system, all of that is the same. Once you need to make a new product, you can be much faster with your response to the market, or maybe to a niche market. Maybe people want a Volkswagen Golf in a specific variant, maybe a little bit longer, or a little bit higher, or whatever. You can be way faster with your production chain because the basics are the same. There are more reasons why this flexibility is a bit increasing now, which have to do with automation. So it's easier to sort of reprogram robots to do something than to train, let's say, 5,000 people to build a new product, right? So also, once things are more robot heavy, it's actually easier to change the logic, because they will just accept your suggestions instead of go against the curve. Can you share more researches? I'll share an article later as well in the email, so you'll find more there. We have to increase automation in all industries. I think that's true. How is RMS different from FMS? Harshit, if you can elaborate what RMS and FMS is, because I don't know the terminology, and then I'll try to respond later. Okay, let's continue. Yeah. So that was the introduction, right? So you can see the journey from the first steam engine, 1802, with very little power, very low efficiency. And now we have Tesla, of course, which can go from 0 to 60 miles an hour in 2 seconds, I think, with the new car. So completely different output, but also a completely different factory. And one thing I would like to mention here is the way this actually happens, because it may feel to you like, hey, this just went in a very smooth line and everything is now here and everything progresses smoothly. But that's actually not how it works. It works in what scientists call punctuated equilibrium, right? Which is, you actually have quite a flat situation. Things are as they are. And then with one invention, that equilibrium that you used to have is punctuated, it's gone. Right. So, for example, Tesla's launch to become, or to have mass-produced electric cars. Suddenly now, that is a new thing. But that happens every time. So if you actually look at the progress period here, you can see that there's a flat line, maybe for 30 years, 40 years. Then there's a new invention, and then suddenly there's a jump. So it's more like a staircase than a smooth line. And this is the same in humanity, right? If you look at our progress, the way we evolved, Whether that includes like key moments like the first stone tool use, or the first fire that people mastered 2 million years ago, or the first cooking, or the first mastery of metals, like the first gold work was done 6,000 years before Christ, right? So those kind of things, they're critical moments, but they're critical in a staircase way, right? Where they suddenly become relevant, and suddenly you have this new capability. Okay, so what kind of tech is involved? Because my guess is quite some of you are interested in technology or come from an engineering background. And this is not a simple story. Like I cannot say, hey, this is all AI driven or all cloud driven, because it's actually a whole range of technologies that makes this possible. We're talking cloud computing, of course, big data, AI, machine learning, augmented reality simulations that you can run, RPA, 3D printing or additive manufacturing, IoT and cybersecurity, right? So all of those things together allow for Industry 4.0. I'll go into them briefly, but for most of them, we have separate webinars where we do way more better deep dives into the topic. And you'll see a little QR code in the top right of your screen. So if you think, hey, this is an interesting topic, just scan it and it will send you to the webinar about it. So first one, and I put those three together: cloud, big data, and AI, right? Critical for Industry 4.0. And they're quite strongly interrelated, right? So the way this currently functions, cloud has a couple of different options, of course: storage, compute, but especially compute power that we're currently seeing is increasing rapidly, and it's democratized, right? So any one of us can spin up a virtual machine in Google or in Azure for Microsoft or in AWS, which means that you have access to this computing power if you pay per hour, right? It's a flexible model. The same is happening with IoT, with sensors. So your iPhone or Xiaomi or Samsung device will have many sensors inside. Your smartwatch will have many sensors inside. Your fridge, your car, anything that you will be carrying in the next, your lights even have many sensors inside, right? So this whole sensorization of society, which then of course produces all the data that is nice to have for AI, that is sort of going hand in hand. And that then means that, you know, if you want to be an AI engineer or a machine learning engineer, that you have a lot of data to work with to optimize those processes. So the first thing to realize, this is actually all connected, right? Cloud, data, connectivity, AI models sort of belong into the same realm. What do they do? What's the essence? Well, the essence of AI is predictive engines, right? So you build something that is able to predict what will happen or what something is. That is typically what AI models do. They have lots of more variants nowadays. Why they're different than classic statistical models? Well, a couple of reasons. They can be way more complex. So if, for example, if you're trying to build a cat classifier or a house price prediction, or maybe in a factory, a predictive maintenance system, when is something going to break down? The neural networks today have way more layers and therefore way more features that they can handle than sort of traditional regression analysis. And of course, they have a built-in feedback loop, right? So once more data becomes available, the model will update itself, will learn, so to say, which means changing the weights, for example, in a neural net, and therefore will become better at the prediction. So the biggest use case of AI in factories is predictive maintenance. What is that? Well, it's predicting when some item in your chain will break. Maybe it's a robot halfway your value chain that will break. Why is that important? Well, if the robot breaks, you have downtime for the entire factory, which can cost you billions, right? And if you know that the robot is going to break in 3 weeks, you can repair it maybe 2 weeks from now. So multiple $billion case, right? Very big case, and it's called predictive maintenance. It uses neural nets, but it's also using something that you may have seen before or not, which is called edge, computing on the edge. And computing on the edge is technically where you do the computation for this AI engine locally, maybe in the robot, or if you're capturing, for example, the vibrations in the wing of an airplane, you do that calculation in the wing of an airplane. Why? Because in many cases, you're measuring quite a simple signal. Maybe it's the vibrations for the engine. And if the vibrations are in this realm, then it's fine. And if they go like this, then you know, hey, something is wrong in this engine, right? So that's anomaly classification system that you would build is pretty simple and can run on a very small computer, which we call an edge device, which looks, for example, like a credit card that you see here on the picture, right? So some of that will happen locally inside the machine, and the bigger jobs, of course, if you have a lot of data that needs to be combined, for example, will go and be computed in the cloud. So you have edge computing, you have cloud computing, but they all do the same thing. In the end, they build predictive models, for example, about predictive maintenance cases. AR, VR, right? So we had a couple of nice webinars on this already. AR is augmented reality, which is when you wear glasses where you can see a little layer on top of reality. So for example, you look at the car and you would see a lot of extra metrics about the car, maybe the heat, maybe the engine efficiency, et cetera, et cetera. And VR is where you have these closed goggles, right? Where you completely immerse yourself into a new world. How is that important? Well, of course, you have real life. So this is the whole classification of the AR, VR space. But augmented reality and mixed reality, you'll see there are lots of use cases in factories, right? There's people walking around with these glasses, Microsoft HoloLens or a different one, and they can actually see better what's happening inside the factory than we can, because they have a digital layer on top of the world that we see. There's a reason why this is growing, of course, right? These glasses are getting better. They're getting also cheaper, right? So some of these things are now in the realm of like 300 euros, which is sort of mass production ready, given that most of our smartphones are probably more expensive than that. And Microsoft HoloLens, which is currently, I think, the best one for factories, is still roughly 3,000 euros. But of course, in the coming years, that will be more accessible. And here you can see an example of how they use these glasses in Kawasaki.
トラブルが発生したときですね、生産が止まってしまうという、そういったシステムの検討というものが非常に大変です。
Azure パーセプトを活用して、今まで気づかなかったような故障であったり、トラブルっていったものや予兆っていったものに気づけると考えております。遠隔地の方にエキスパートの方がいてくれるだけで、一つの作業現場に技術力であったり知見っていったものを流すだけではなくて、複数の作業場っていったところに提供しまして、そうすることによって即時にトラブルシュートを迅速化できます。
それが、デジタルツインの世界ができますと、実際現場に行かなくてもそのトラブルの状態が手に取るように分かって、そこでもう直すことができると。そういったものがですね、仮想空間の中で全部調べれるようになります。
完全なるメタバースの世界は、開発から設計ないしは試験までのすべての工程っていうものを仮想環境上で実行できます。
Okay, so maybe to give you a bit of a sense of what you were actually seeing here, right? So Kawasaki is one of the main robot producers on the planet, Japanese, of course. And you're seeing two different things. The first thing is someone with an AR device, right? These glasses where you can see through, inspecting a robot. And what is she seeing? Well, she's seeing a couple of metrics that otherwise would not be available. And how can she see that? Because there are sensors inside the robot that track that. And once you get close enough, it will stream to the device, right? So that makes it much easier to repair. It makes it much easier to know what's going on in your factory and inside every robot. The second thing you're seeing, which is the screen that's currently still here, is a virtual simulation of the device. This is the virtual twin, right? So it's the same robot you see here on the table, but it's a virtual copy that they can play with and optimize here in this VR environment. So both of these applications, one is VR, one is AR, but both are virtual reality applications that can help to optimize this machinery. Let me respond to the questions. I'm not so Harshit. Sorry, I cannot answer your question because I don't know these things well enough. So Harshit asked, how is RMS different from FMS? And RMS is reconfigurable manufacturing system. FMS is flexible manufacturing systems. And I don't know the answer. That's sorry what I have to tell you. I'm only doing the introduction here for Industry 4.0. I'll make sure we have some better speakers later on. The QR code of some of the former webinars is not working. I'll send you also the links later in the email. So if it didn't work so far, I'll make sure you have the link. And how do you see this happening in pharma? Kushman is asking. So I think many things are the same because I'm trying to get to the level of principles and basic technologies. maybe with some additional difficulties for pharma, right? Because pharma, of course, has very high quality standards and therefore has way more regulation. So typically what I've seen is that they move a bit slower and they're a bit more cautious, where someone like Elon Musk, for example, would move faster and just build it regardless. But I think lots of the principles at Kuzman would be the same. Okay. Simulations, and this is, you just saw it happening. You just saw that they had a simulation of a robot in VR, and typically that happens through virtual twins, and that's a concept you should really remember, right? So a virtual twin is a virtual copy of the real thing. And if you buy a Tesla, for example, you have the Tesla in your garage, but Musk and his team will have a virtual copy of your Tesla in their database. And that means they will test things first on that virtual copy. Why? Well, because you eliminate many risks, it's faster, it's cheaper, etc. So this is the beginning of virtual twins, but now you see a different phase where you can actually build entire factories as virtual twins. So not just a single car, but maybe the entire car factory. Why would you do that? Again, same answer, to optimize that factory. Let me show you. This is NVIDIA. NVIDIA is not in the game of building factory optimizations, but it's in the game of building these kind of omniverse tools and SDKs, as they call it. But this is a tool that allows you to make your own factory digitally and then optimize it there before you build this. And large car makers like BMW this is how they currently optimize the factories that they have. Okay, let's keep it there. I think you get the picture here. So why is this relevant, right? Now you're building digital twins that are going beyond a single robot, going beyond a single car. Now you're actually building your factory virtually first before you actually start using it. And you can mathematically optimize it as far as you want before you put your real money in, right? So this is, I think it's groundbreaking. And the fact that Tesla, BMW are using this, it's very different than the Ford, let's have everybody at the assembly line model, right? This is a mathematical optimization game now in a virtual physics-led environment. So RPA, we've done a webinar here, and I would definitely recommend, because the guy we had speaking was one of the biggest talents we have in RPA in the Netherlands. RPA is where you use software robots to automate repetitive work, right? So that's typically work that is high volume, low complexity, like filling Excel sheets, transferring data from A to B, typing simple responses. It's extremely relevant because this is a situation where many of us are still doing the same work day in, day out. Even for me, I'm still doing a lot of stuff that I think is completely automatable and should be automated, right? So I have more time to do things like this that I enjoy. So that's RPA. These are automation layers. You can call them software robots. They can learn from your actions. So if you use a good platform like UiPath or one of these bigger players, things that are repeat tasks for you, they can learn actually from your behavior. And therefore you can build these little software robots. I'm not going to go in, Bas did that already in the webinar. If you really want to learn this, you can go to UiPath. They have a whole academy for this. This is about repetition tasks that are happening at a large scale that you can automate. The beginning was that your employer would automate that, and now it's actually in a situation that lots of people are trying to do that themselves because they also want more interesting jobs versus doing the same stuff day in, day out. Additive manufacturing. This is, I think it's a key thing that you may have seen. This is how you 3D print materials. Here on the left, you can see the market size. So it's still pretty small. In practice, this is still, so it's a $12 billion market. Yes, it's a lot of money, but it's still very much in the early stage. And it will sort of go ×3 in the next 5 years, right? You can see a lot of sort of shifts happening there. Also the materials you could use. First, it was only plastics. Now it's also titanium and different steel types. What is it used for? Well, for example, product development, right? So building something that is unique with a special product that you could not build in a different method. Let me show you. This is a steel 3D manufacturing plant where you can see they build a very custom item. I think it's for an airplane, but I'm not 100% sure. But you can see this process happening.
It's the same part I've ever printed in my life. The machine delivered. So the cool thing about this machine is we can manufacture parts like this that would be impossible using traditional manufacturing methods without a lot of design changes and assembly steps. And we did it completely unattended. I went and handled other tasks. I came back, I raised the part out of the powder bed, and I was blown away at the level of detail that it achieved. So from here, we're gonna have to cut our part off our build plate. To help with that, we added a little bit.
So of course, this is a sales pitch, right? But you can see a lot of the things here, which I think are quite amazing, right? This kind of unique item would be very hard and very, labor intensive to make if you did not have a machine like this. There are also still risks, right? Like the reason why 3D printing is still not completely happening at scale is not everything is working as smoothly as you want. For example, quite some of these steel devices still don't have the strength of the devices we build otherwise. So they break more easily. So there's stuff that we still need to improve. I can send you more materials on this if you like. But this is, of course, coming up. And it allows for making unique items like this or mass producing specific items. But mostly, I think the uniqueness of like how precise can you put in your CAD, your computer-aided design, and what do you actually get back, I think is quite fascinating. IoT, so Internet of Things, how to understand this. Let's make it very easy, right? Internet of Things is about sensors. Sensors produce data. With data, you can then make better predictive models. So IoT is technically sensorization of the world, right? And a lot of there are hundreds of different types of sensors. If you go to Alibaba, for example, you can buy many of them. This kit I bought myself. It gives you 37 sensors. It was like 40 euros. Of course, they're not the best, right? They're a bit large. But you can see how many different sensors there are and how cheap they can be. So you're talking about cents per sensor, right? So that's the logic there. They can have different kind of connectivity, right? They can have, of course, different ways and different signals. But the logic is these sensors produce data that you can then use for a more intelligent factory. Last thing, cybersecurity. I'm just going to mention it briefly before we look at some more interesting things. This is more node, right? Obviously, with a factory having more data and the data being proprietary and sometimes confidential, there is a larger risk of data breaches and risk to cybersecurity. So this is more a risk statement than an actual how does it work. But we have a good webinar again here as well if you want to deep dive. Let me check the time for a second because I have, okay, good. We still have some time because I had no clue what time it was. I still want to do one more thing with you. And I think now you got the message, okay, this is where we come from. This is the technology that's involved, but there is one more thing, and that is, why does this actually matter to you as a person? So maybe if you want to go in manufacturing, okay, super helpful, but why does it matter for normal people like us? So one thing is that it allows for a combination of mass production, like Ford Model T, you have one chain, everything, they all make the same cars, into a mix now of mass production plus mass customization. And an example here is, I took this yesterday, this is Nike, right? You go to the Nike website and you say, I want sneakers, but I want to change the colors for every item. So it's not full mass customization because you cannot build the sneaker entirely yourself, but you can choose the colors, you can choose lots of different tiny little things that will be different. But of course, this will be mass produced, right? There's not a single person going to make your sneaker if you change the color. So you can see the first items here that are both becoming customizable as well as factory made. Why is that important? Because people pay more for custom products. And I'm not sure about you, but if you get custom sneakers or custom shirts or custom watches or whatever is actually made for you, there's a premium that people tend to pay. For clothing, that can be, let's say, 25% or so, footwear, 25%. So it's roughly in that range, right? So let's say 15 to 25% that people are willing to pay more, which is really significant if you think about making products for the world, right? If you can sell them for 25% more, of course, that's a massive business case. So this is one of the things that you'll see, that people will be wearing stuff that's actually made uniquely for them. And if you plot that, and this is a chart I got from an MIT professor that I used to study with, you can see that it's actually a unique situation, right? So we went first from making single products that was actually made by one expert, maybe a bow and arrow that only one guy in your tribe could make because he was the bow and arrow expert. That is how we started with craftsmanship. Then we went to the situation that, okay, these machines got more complex, like the steam engine. But then, of course, everything became an optimization for mass production, right? You can see here this production rate going higher and higher. This is the whole Ford Model T Toyota situation. And now we're at this stage where, hey, maybe we can have both a high production rate as well as more product variety, so more customization, which is you can call it hyper differentiation, you can call it personalization, you can call it customization, but it's quite a unique situation that maybe we can do both with the amount of data that we have. For companies, and I think this is almost my last slide, I have one more. For companies, that means that they will really change how they do business. And if you read The Economist or you read Financial Times, you'll see a lot of those items that I mentioned here come back every day. Right, so the 3.0 standard, what do? You make mass-produced same items. So Kimo water bottles, we make 1 million of those, they're all the same, right? Of course, you want that to be cheap. So you do that not in the Netherlands, for example, where prices are high, but you do it in a place where prices are low. So you offshore the production. Quite often, you have lots of different suppliers. So with this bottle, of course, you don't, but with an iPhone, you might have hundreds of different suppliers for every element. Therefore, you have this big inventory planning game that you need to do. And if something goes wrong, it's very costly. The 4.0 variant is that you want to be able to make custom, more premium products. And that means you want more control, right? You want to have a better sense of what's happening. So that might mean reshoring production, bring it closer to where you are, so you have a better sense of how things actually work. Some items might be produced with 3D printers. For steel, that might be actually very expensive machines. Another reason to bring it closer to home. The supply chains, like where do you get stuff from? In the beginning would be quite difficult to know where your container would be. For example, now, of course, everything is completely traceable. So you would have real-time data where every chip that you're waiting for is located. And of course, we have lots of AI models that can actually predict how efficient, what the throughput will be for your factory, right? So this is a different thing where factories come closer to home, where companies want more control. And in the end, they have a reason to build more custom, more premium products. So for the distribution, you see the same thing. A lot of warehousing now is moving closer to the end user, where in the beginning, they would be optimized for cost. Distribution is more localized for speed. I'm not sure about the places where you guys live, but here in the Netherlands, we have this new 10-minute delivery hype, which means you can order everything and you get it within 10 minutes. And that's done for supermarket products, right? But that means, of course, that the warehouse is sitting pretty much next to your home, right? Otherwise, you cannot do that. Warehouses are mostly led by robotics, and delivery, of course, in the future will be partly autonomous, right? Whether that's Amazon's drones or the self-driving cars or whatever. But that's the distribution logic that will also change. And the last thing I think very important, in the past, you had this chain where people would make stuff, then you have wholesalers, etc. in between, and in the end, you have the consumer. But the data of the consumer would not always go back to the initial producer. So they would produce it pretty much in the dark, hoping that the end user would like it. And of course, now everybody is trying to go for a D2C, direct-to-consumer model. Why? Because then you can actually learn from consumers. So the data you want to capture, instead of a middleman capturing your data and learning more than you learn. Right? So this whole logic of selling it to wholesalers, retailers, and selling it to customers, the ideal model most consultants would recommend is find a way to go direct to consumers, find a way to get the end user data so you can build more custom, you can learn faster, right? And build that relationship with that user group. Final slide, and I think really relevant. So what happens? So forget looking at the slide because the slide is a bit complex, but what happens if you have all this stuff in place? So think about having a factory with all these sensors in place, thinking about having products with all these sensors in place, right? What happens? Well, what happens is that you know how things actually work. So if you have a car on the road, you have the usage data for that car. If you have a tractor in the field, you have that usage data. And that means you can have a lot of new business models attached to your product. For example, let's say you're a farmer and you need to buy a new tractor to work your field, right? How much is a tractor? How much would you need to invest? Maybe 500,000 euros, something in that line. It's a lot of money. They would need a mortgage for it, right? Super risky investment. But if the situation now is that we actually know how many hours that tractor rides in the field, then someone else could make that investment and rent out this tractor per hour, right? So this is called sort of the new servitization of products, where you don't need to do the initial investment, but where you can pay per hour for the usage of something. Is it relevant? It's extremely relevant because it means that a lot of people with less money to spend could now rent products that otherwise they would not have access to. You see this in lots of different ways. You see it hardware as a service, for example, this tractor, or a Rolls-Royce, who makes, for example, plane engines. Their new payment model is power by the hour. So you actually pay for the amount of time your plane is in the air, right? Which is completely different than buying the engine. Of course, software as a service, right? That we all know. So you pay for the usage of the software. You don't have to buy the disk. You just pay for maybe the accounts or the time spent. Infrastructure as a service, which is, for example, GCP, right? Where you can run virtual machines and you pay for the uptime of the machine. And platform as a service, which are multi-function platforms in the cloud. So all of these are all service models that can only run because the data they have is real time. Examples that you may or may not know, right? So Rolls-Royce, plane engines already mentioned. How do these these companies pay? They pay for the uptime of the engine, right? So plane in the air, you pay, plane on the ground, you don't pay. Completely different. But even tires in your car, right? So how many usage hours do you get, and you pay for those usage hours? That's Michelin. Right, so all these things are now moving towards a service-led model. Interesting for all parties because the companies will get more data, people pay their fair share without doing the risky investment. And that's the other side of this whole transformation. Okay, how much time do we have left? A few minutes. I hope you learned something, at least on some of the slides. Let me have a quick look at the questions before we sign out. Okay, the links don't work. Sorry for the QR codes that didn't work. What effect do you think Industry 4.0 will have on the mining industry? I think, so in mining, what I know, there's a lot of geotagging and a lot of AI involved, right? To optimize these driving routes for cars, for example. But I'm not familiar enough to say that this will really transform the way that system works. I'm not familiar enough with mining, but I know there's a lot of stuff going on with optimization of fuel for all these cars driving back and forth. And of course, that is then based on having sensors for fuel, having some kind of GPS system, where you can tell drivers don't go too fast, don't brake too much, all of those kind of things. So that is becoming more real time, but that's as far as I know. Ali, I don't know enough about quality 4.0, like the sub things. So I haven't seen that specifically, but I'll share some more info. What are thesis possibilities about this topic? any problem one can work on. That's a very interesting one. I think there are many actually, but I think, Hassan, your thesis should be about Industry 5.0. So this 4.0 is what we're currently in the middle of. But I think the more interesting question is what will happen 5 to 10 years from now. So I would suggest, if you write a thesis, take this as a given and think about what is coming next after this. There are a couple of blogs already there, but it's still preliminary. But I think that would be the more interesting question. Presentation will be shared. Meaning of ASM. I'm not sure where I mentioned ASM. So I'm not sure what it is. There's way too many of these little phrases and keywords in this industry. What's the additional cost to migrate to 4.0? That is also a great question. I think this is not a binary transition, right? So if you have a factory now, you're not going to be 4.0 tomorrow morning. So what I think will happen is very specifically that we'll start with like very feasible, high impact initiatives. So maybe one robot always breaks down and we need to have more data about that robot. So you first start there on a very critical point where you have to install some sensors there to understand what's going on. So I think that's the way it will go in practice. I don't think anyone will really, unless you're Elon Musk and you build a factory now, so you can build the whole thing from scratch. But otherwise, you'll probably look at like, where can I optimize first? So you would actually do that in stages, starting with the low-hanging fruit that you need to get. And in that sense, it would not be that expensive because you can move step by step, and your ROI should be positive, of course. Right. So that is the logic. Internship opportunities at Kimo. Sorry, not at the moment. Yeah, this is a great question. What is the Kpis shift 3.0 to 4.0? So the Kpis shift, that is a really smart question. That's what I was trying to say here. So Kpis, by the way, is capital investment, right? So that means that the investment that you do upfront, maybe to buy a tractor or to buy a plane or to buy an engine. And Kpis is typically where you would need to get some kind of financial arrangement for, right? Because if you're a farmer, maybe your annual salary is 100,000 euros or whatever, but the farm or the tractor would be very big expense for you. So that's Kpis. And what I'm saying here on this slide is that a lot of the Kpis would become OpEx, right? So OpEx are operational costs that you have running your factory. So you don't need to put the money in upfront. With the service model, you just pay for the usage, which means Kpis then shifts to OpEx. And if the ROI, of course, is good, maybe as a farmer, you have more output with the tractor, then you could pay that back on a more regular basis. So that's a smart question. Thanks for that. That's what I was trying to say. So many questions on the list. Let me do one more, and then I'll email you, and I hope to see you again so we can have more conversation. How is this version decided? 4.0, 5.0, etc. Last question, and it's nice to go back to the beginning of the whole terminology. So Industry 4.0, just a German term for this transition, right? So the German leadership decided to call it that. And so technically it's a bit subjective, right? There's no one really saying, hey, now we're in 4.0, now we're in 5.0. Japan already calls this 5.0. But the clusters I showed you in the beginning, let's look back to where we were, right? This is a typical clustering that you'll see in these books, because they're quite big jumps in how we were producing stuff, right? So this is very much focused on single people or small teams with a lot of expertise building something. Then this mass production is really focused on making the same stuff that all looks the same in a assembly line. And then here we suddenly have IT, and we have systems, and we have management, and we have all these principles that are involved. And then finally, of course, in 4.0, we have this whole cyber physical production system. So just clusters that seem to make sense because the technology really changed in those clusters. But there's no authority that says, now we're moving from A to B. Okay, guys, I hope it was useful. I hope you enjoyed it and you learned something. Get a certificate with the link, and hopefully we'll meet again in the next webinar. Bye.